Grand Canyon National Park. National parks in the USA. The Grand Canyon is often described not merely as a landscape, but as a planetary event. Standing on the rim, one does not simply look across a valley. One looks down into the interior of the earth and backward into the abyss of deep time. Located in northwestern Arizona, this colossal chasm is the centerpiece of Grand Canyon National Park, a protected area that encompasses 217,403 acres of the Colorado Plateau. It is not the deepest canyon in the world, nor is it the widest, but it is universally acknowledged as the most intricate and visually overwhelming example of arid land erosion on the planet. The park was officially designated in 1919, yet its existence as a protected reserve began earlier under the guise of a national monument, championed by President Theodore Roosevelt, who famously declared it the one great sight which every American should see. The park protects a substantial portion of the Colorado River's 277-mile journey through the canyon, preserving a vertical cross-section of geologic history that spans nearly 2 billion years. This is a place where biological and geological worlds intersect with violent beauty, creating a natural laboratory that has informed our understanding of erosion, speciation, and the very age of the Earth. To understand the identity of Grand Canyon National Park, one must first grasp its geographic setting. The park sits atop the Colorado Plateau, a massive, uplifted tectonic block that covers the Four Corners region of the American Southwest. This plateau is geologically stable, meaning the rock layers have remained relatively horizontal despite being lifted thousands of feet above sea level. This horizontal layering is what gives the canyon its distinctive architectural appearance, resembling vast temples and sunken pyramids. The park is divided into two distinct primary areas based on access and geography: the South Rim and the North Rim. The South Rim, averaging about 7,000 feet in elevation, is more accessible and arid, covered in pinyon juniper woodlands. The North Rim, located only 10 miles away as the Raven flies but over 200 miles by road, stands significantly higher, averaging over 8,000 feet. This elevation difference creates a dramatic climatic disparity. The North Rim receives significantly more precipitation and supports dense forests of aspen, spruce, and fir, resembling the biology of Canada more than the desert of Arizona. The defining feature of the park is, of course, the canyon itself. It varies in width from roughly 4 to 18 miles and reaches depths of over a mile or about 6,000 feet. The mechanism of its creation is a subject of both settled science and ongoing research. The primary agent of incision is the Colorado River. The river functions as a high-powered conveyor belt for sediment. It is not water alone that carves the rock. It is the sand, gravel, and boulders suspended within the turbulent flow that act as a liquid sandpaper, scouring the riverbed incessantly. While the river cuts downward, other forces widen the canyon. Weathering, gravity, and the freeze-thaw cycle attack the canyon walls. In the winter, water seeps into cracks in the rock, freezes and expands, shattering the stone. Gravity then pulls the debris down into the river, which flushes it away to the sea. This process of mass wasting ensures that the canyon does not remain a narrow slot, but widens over millennia into the terraced spectacle seen today. The geologic narrative exposed by this erosion is the most complete record of Earth's history found anywhere on land. As visitors descend into the canyon, they are traversing a timeline. The rocks at the rim, known as the Kaibab limestone, were deposited roughly 270 million years ago during the Permian period, when this region was the bottom of a shallow, warm equatorial sea. Fossils of brachiopods, sponges, and mollusks are embedded in this creamy white rock, evidence of a marine environment that predates the dinosaurs. Below the Kaibab lies the Toroweap Formation, followed by the Coconino Sandstone. The Coconino creates a sheer, white cliff face visible from miles away. It is composed of petrified sand dunes, the remnants of a vast, Saharan-like desert that covered the region. Cross-bedding in the rock preserves the angles of ancient wind-blown dunes, freezing the direction of Permian breezes in stone. Descending further, the geology changes in color and composition. The Hermit Shale forms a red, sloping layer, rich in iron oxide, which rusts on contact with the atmosphere, staining the cliffs below. Beneath this lies the Supai Group, a mix of sandstones and siltstones deposited in swampy coastal environments. Then comes the Redwall Limestone, one of the most prominent cliff-forming layers in the park. Though the rock is naturally gray, it is stained crimson by iron-rich water dripping from the layers above. The Redwall is riddled with caves and solution caverns, a testament to the solubility of limestone in slightly acidic groundwater. Below the Redwall is the Tonto Group, consisting of the Muav Limestone, Bright Angel Shale, and Tapete Sandstone. The Bright Angel Shale is softer and erodes more easily, creating the broad, flat Tonto platform that separates the inner gorge from the outer cliffs. This platform serves as a major ecological niche and a pathway for hikers and wildlife. At the very bottom of the canyon, the river cuts through the oldest rocks of all, the Vishnu basement rocks. These consist of the Vishnu schist and Zoroaster granite. Unlike the flat sedimentary layers above, these rocks are twisted, dark, and vertical. They are metamorphic and igneous rocks, remnants of ancient mountain ranges that were forged under immense heat and pressure about 1.7 to 1.8 billion years ago. They represent the roots of a mountain chain that may have once rivaled the Himalayas. The contact point between these ancient basement rocks and the sedimentary Tapete sandstone sitting directly atop them is known as the Great Unconformity. This boundary represents a geologic mystery, a missing gap in the rock record, spanning roughly 1.2 billion years. There is no record of what happened here during that vast stretch of time. The rock was either never deposited, or, more likely, was eroded away completely before the Tapete sandstone was laid down. Touching this line means spanning a billion years with the width of a finger. The biological reality of Grand Canyon National Park is as layered as its geology. The park is often described using the concept of life zones, a system developed by C. Hart Merriam in roughly this very region in the late 19th century. Merriam observed that changes in elevation mirror changes in latitude. Hiking from the Colorado River to the North Rim is ecologically equivalent to traveling from the deserts of Mexico to the boreal forests of Canada. Within the park boundaries, there are 5 major life zones: the Lower Sonoran, Upper Sonoran, Transition, Canadian, and Hudsonian zones. This vertical compression of habitats allows for an immense diversity of species to coexist in a relatively small geographic area. At the bottom of the canyon, along the river corridor, lies the Lower Sonoran Life Zone. This is a true desert environment. Summer temperatures frequently exceed 120 degrees Fahrenheit, and rainfall is scarce. The vegetation here is adapted to extreme heat and drought. Cacti, including the barrel cactus and prickly pear, dominate the landscape, utilizing specialized photosynthetic pathways to conserve water. Agave and yucca plants cling to the rocky slopes. The agave, or century plant, spends decades storing energy in a fleshy base before sending up a massive, singular flower stalk, dispersing its seeds, and then dying, a reproductive strategy known as semelparity. The riparian strip along the river offers a stark contrast to the surrounding desert. Here, Thanks to the permanent water source, willow and tamarisk thickets grow. It is important to note that the tamarisk is an invasive species introduced in the 19th century, which has outcompeted native willows in many areas, altering the soil salinity and channel dynamics. Ascending from the river, one enters the upper Sonoran zone, which encompasses the Tonto platform and the middle slopes of the canyon. This area is characterized by a pygmy forest of pinyon pine and Utah juniper. These trees are incredibly hardy, capable of surviving in thin, rocky soil with minimal moisture. The juniper acts as a drought survivor, able to shut off fluids to specific branches during extreme water stress, effectively self-pruning to keep the core of the tree alive. This zone is also home to blackbrush and sagebrush communities. The biological crust of the soil here is a critical, often overlooked feature. Known as cryptobiotic soil, this knobby black crust is a living community of cyanobacteria, lichens, and mosses. It binds the loose sand together, preventing erosion, and fixes nitrogen from the atmosphere, fertilizing the soil for other plants. It is incredibly fragile. A single footstep can destroy a crust that took decades to form. Reaching the south rim at 7,000 feet, visitors enter the transition zone. The defining species here is the ponderosa pine. These majestic trees have thick, puzzle-piece bark that smells of vanilla or butterscotch when warmed by the sun. The bark is an adaptation to fire. It flakes off as it burns, carrying the heat away from the living cambium layer of the tree. Natural, low-intensity fires are a crucial part of this ecosystem, clearing out underbrush and allowing the seeds to germinate. In the absence of fire, the forest becomes overcrowded and susceptible to catastrophic crown fires. The understory of the ponderosa forest includes gamble oak and mountain mahogany, providing distinct food sources for herbivores. The North Rim, rising to over 8,000 feet, hosts the Canadian and Hudsonian zones. Here, the air is cool and thin. The ponderosa pines give way to dense stands of Engelmann spruce, subalpine fir, and quaking aspen. The aspen groves are actually single organisms connected by a vast underground root system. An entire hillside of trees may be genetically identical clones. In the autumn, the North Rim transforms into a ribbon of gold as the aspen leaves turn, a sharp contrast to the evergreen conifers. This high-elevation island is isolated from similar environments by the sea of desert surrounding it, leading to unique evolutionary pressures. The meadows here receive heavy snowfall in winter, which melts slowly, recharging the aquifers that feed the springs emerging thousands of feet below in the canyon. The fauna of Grand Canyon National Park is as diverse as its flora, with animal populations strictly segregated by the canyon's physical barriers. The canyon acts as a formidable obstacle to genetic exchange for many small mammals. The most famous example of this evolutionary divergence involves the squirrels of the canyon. On the North Rim lives the kaibab squirrel, identifiable by its dark body and pure white tail. On the South Rim lives the Abbott squirrel, which has a gray body and white underparts. They share a common ancestor, but became geographically isolated as the canyon widened and deepened. Over millennia, unable to cross the hot desert environment of the inner canyon or the river barrier, they evolved into distinct subspecies with different physical characteristics. This phenomenon, known as allopatric speciation, is vividly illustrated here. Larger mammals, however, can navigate the terrain with greater ease. The desert bighorn sheep is the icon of the inner canyon. These animals are marvels of biological engineering, adapted to traverse the sheer cliffs and unstable scree slopes. Their hooves are concave with sharp edges and rubbery pads, allowing them to grip rock surfaces that seem vertically impossible. They can go for extended periods without water, obtaining moisture from the vegetation they consume. Mule deer are common on both rims, often seen grazing in the forests at dawn and dusk. They migrate vertically, moving to lower elevations during heavy winter snows and returning to the high rims in summer. The park is also home to mountain lions, the apex predators of this ecosystem. These elusive cats regulate the populations of deer and elk, maintaining the balance of the food web. Though rarely seen, their presence is vital to preventing overgrazing and disease spread among ungulate populations. The avian life of the Grand Canyon is dominated by the masters of the air. The most significant conservation story in the park belongs to the California condor. One of the rarest birds in the world, the condor was brought back from the brink of extinction through a captive breeding program and reintroduced to the Vermilion Cliffs and the Grand Canyon area. With a wingspan reaching nearly 10 feet, these scavengers rely on the thermal updrafts generated by the canyon's heating walls to soar for hours without flapping their wings. They are nature's cleanup crew, feeding exclusively on carrion. Their recovery is ongoing but threatened by lead poisoning. Condors ingest lead bullet fragments left in game piles by hunters outside the park, which is often fatal. Seeing a condor glide over the abyss is a connection to the Pleistocene era, a glimpse of a time when giant teratorns ruled the skies. Raptors of all kinds thrive here. Peregrine falcons nest in the high cliffs, utilizing the vertical space to hunt. They are the fastest animals on the planet, diving at speeds of over 200 miles per hour to strike prey in midair. The acoustics of the canyon allow the calls of canyon wrens to echo melodiously against the stone walls. This small bird, with its cascading song, is often heard before it is seen, flitting among the rocks of the inner gorge. The Colorado River itself hosts a unique and imperiled ecosystem. Before the construction of Glen Canyon Dam upstream in 1963, the river was warm, muddy, and prone to massive seasonal floods. The native fish evolved to survive in this turbulent, opaque environment. The humpback chub, an endangered species, has a pronounced hump behind its head that acts as a hydrofoil, helping it maintain position in the rushing currents. The razorback sucker and the Colorado pike minnow are other native species adapted to these specific conditions. However, the dam changed everything. It releases clear, cold water from the bottom of Lake Powell. This cold water disrupts the reproductive cycles of native fish, which need warm water to spawn. Furthermore, the clear water favors visual predators like non-native trout, which were introduced for sport fishing and now prey upon the native species. Conservation efforts are underway to simulate artificial floods and manage invasive species to give the native fish a fighting chance. Hydrology in the Grand Canyon is not limited to the Colorado River. The park is home to numerous springs and seeps that emerge from the canyon walls, creating hanging gardens. These microhabitats are oases of ferns, mosses, and monkey flowers in the midst of vertical deserts. The water that feeds these springs originates as snowmelt and rain on the rims. It percolates down through the porous limestone and sandstone layers until it hits an impermeable layer, usually the Bright Angel Shale. Unable to move downward, the water flows horizontally until it breaches the cliff face. The most spectacular example of this is seen in the tributary canyons like Havasu Canyon, located on Havasupai land adjacent to the park, and at Thunder River, The water in these side canyons is often rich in calcium carbonate. As the water degasses and flows over vegetation, the calcium carbonate precipitates out, forming travertine. This rock builds up over time, creating natural dams and terraced pools of stunning turquoise water, a stark contrast to the often muddy flow of the main stem of the Colorado. The climate and atmospheric conditions of the Grand Canyon are integral to its natural identity. The park experiences a bimodal precipitation pattern. Winter storms from the Pacific bring snow to the rims, which is critical for the long-term water supply. In the summer, the North American monsoon shifts wind patterns, drawing moisture up from the Gulf of California and the Gulf of Mexico. This results in violent, localized thunderstorms in July and August. These storms are dramatic and dangerous. Lightning strikes the rims frequently, and flash floods can turn dry washes into raging torrents in minutes. The visual clarity of the air is a prized resource of the park. On a clear day, visibility can exceed 100 miles, allowing visitors to see mountains in southern Utah. However, regional pollution and fine particulate matter can cause haze, reducing visibility and dulling the vibrant colors of the rock layers. One rare and ethereal weather phenomenon that occurs in the park is the total cloud inversion. This happens typically in the winter, when cold air is trapped in the canyon by a layer of warmer air above a temperature inversion. If there is sufficient moisture, the entire canyon fills with clouds, leaving only the island-like tips of the highest buttes and the rims exposed. To an observer on the rim, it looks as though the canyon has been replaced by a white ocean, with the tops of rock formations jutting out like jagged archipelagos. The Grand Canyon's natural soundscape is another protected resource. In the remote backcountry and side canyons, the silence is profound, broken only by natural sounds, wind, water, and wildlife. This acoustic environment is considered a critical part of the wilderness character. The lack of anthropogenic noise allows for the survival of species that rely on sensitive hearing for hunting or avoiding predation. However, the management of air tours and overflights is a constant balancing act between visitor access and the preservation of natural quiet. The ecological interactions within the park are driven by the harshness of the environment. Scarcity defines the food webs here. In the desert zones, everything is potential food or moisture. The interactions are often a biological arms race. Plants develop spines and toxins to deter herbivores. Herbivores develop specialized mouths and digestive systems to overcome these defenses. The collared lizard, a colorful reptile of the rocky slopes, hunts insects and smaller lizards, utilizing the heat of the sun to fuel its metabolism. In turn, it must avoid the Great Basin rattlesnake and the Grand Canyon rattlesnake, an endemic subspecies with a pinkish hue to match the rocks. The balance is delicate. A wet winter leads to a bloom of wildflowers, which supports a boom in insect populations, which in turn feeds the lizards and birds, eventually supporting the raptors and coyotes. A drought year sends shock waves through the entire system, reducing reproduction rates across the board. The dark skies of Grand Canyon National Park are a natural feature as significant as the geologic ones. The park was designated an International Dark Sky Park in 2019. Far from major cities, the lack of light pollution allows for a pristine view of the cosmos. This is not merely an aesthetic asset. It is a biological necessity for nocturnal wildlife. Many species, from bats to moths, rely on natural light cues from the moon and stars for navigation and foraging. Artificial light can disrupt these circadian rhythms and migratory patterns. The preservation of darkness allows for the observation of the Milky Way in a detail that has been lost to much of the developed world, connecting the geological deep time of the rocks below with the astronomical deep time of the stars above. The caves of the Grand Canyon represent a final frontier of exploration within the park. Thousands of caves are estimated to exist within the Redwall limestone, but only a few hundred have been documented. These caves are time capsules. Because the environment is so dry and stable, biological remains are preserved for tens of thousands of years. Scientists have found the mummified remains of Shasta ground sloths, extinct mountain goats, and condors within these caverns. Pack rat middens, solidified piles of plant matter, and waste collected by rodents over millennia provide paleobotanists with a precise record of how the vegetation of the canyon has changed since the last ice age. By analyzing the seeds and pollen trapped in these amber-like formations, researchers have reconstructed the shift from a cooler, wetter climate dominated by juniper and biological diversity to the modern arid desert. The scale of Grand Canyon National Park challenges human comprehension. It is a place where rock flows like water over millions of years, where a river acts as a chisel, and where life clings to the margins of existence with tenacity. The interplay of uplift, erosion, and climate has created a landscape that is both a barrier and a refuge. It is a vast, open book of the Earth's history, typically read from the bottom up, telling a story of mountains raised and raised, of seas advancing and retreating, and of the persistent power of water and gravity. From the oldest schist at the riverbed to the Kaibab limestone at the rim, and up to the ponderosa forests and the soaring condors, the park functions as a holistic, integrated system. The physical separation of the north and south rims creates distinct biological islands, while the river corridor serves as a tenuous artery of life in a stone wilderness. While the geological architecture of the Grand Canyon tells a story of deep time measured in billions of years, there is another layer of history here, far more recent but no less profound, written in the dust of the canyon floor and the alcoves of the high cliffs. This is the human history of the canyon, a narrative that transforms this geological spectacle into a cultural homeland. For thousands of years, long before it was mapped by Powell or protected by Roosevelt, the canyon was a place of residence, worship, farming, and trade. To view the Grand Canyon solely as a natural park is to overlook its identity as a lived-in landscape, a place where human ingenuity adapted to one of the most rugged environments on Earth. The silence of the canyon is deceptively empty. In reality, it echoes with the ancestral voices of at least 11 sovereign tribal nations who maintain deep, ongoing cultural connections to this space. The human timeline in the Grand Canyon stretches back to the waning days of the last ice age. Paleo-Indian hunter-gatherers, the makers of Clovis points, traversed this region as early as 12,000 years ago, hunting megafauna like the mammoth and giant ground sloth. However, the physical evidence of these earliest inhabitants is scarce, often limited to isolated stone tools found on the rims. A more distinct and mysterious archaeological signature emerges from the Archaic period, roughly 2,000 to 4,000 years ago. These people left behind split twig figurines, one of the most enigmatic artifacts of the Southwest. Found primarily in dry, inaccessible caves within the Redwall limestone, these small figures are constructed from single willow or squawbush twigs, split and carefully wrapped to resemble deer or bighorn sheep. Interestingly, these figurines are rarely found in association with habitation sites or daily trash. Instead, they are located in caches in remote caves, sometimes pierced with small sticks, suggesting a ritualistic function. The prevailing scientific theory posits that these were totems of hunting magic, placed in the Earth's womb to ensure the success of the hunt or the abundance of game. They represent an early spiritual engagement with the canyon's fauna, acknowledging the difficulty of survival in this vertical terrain. As time progressed towards the first millennium AD, the canyon witnessed the rise of agricultural societies. The ancestral Puebloan people, often historically referred to as the Anasazi, inhabited the canyon, particularly the eastern portions and the south rim. Simultaneously, the Kohonina culture occupied the lands south of the canyon. These were not merely nomadic wanderers, but settled farmers who performed a feat of agricultural engineering that seems nearly impossible today. They farmed corn, beans, and squash in the bottom of the canyon and on the high rims. In the inner canyon, where temperatures soar and water is localized, they utilized every drop of moisture. They built check dams across small drainages to catch sediment and water during storms, creating terraced garden plots. They planted crops near springs and seeps, maximizing the limited arable land. The architectural legacy of the ancestral Puebloans is visible throughout the park. Granaries used for storing surplus grain and seeds are tucked into high alcoves and cliff faces, protected from rodents and the elements. The Nankoweap granaries, located high above the river in the eastern canyon, are a prime example. These masonry structures, perched on a sheer ledge, required a treacherous climb to access, signaling the value of the food stored within. The presence of corn cobs and pottery shards near these sites confirms a complex society that had mastered the art of living in the stone. For the contemporary Native American tribes associated with the park, the Grand Canyon is not an abandoned ruin, but a sacred living entity. For the Hopi people, the canyon is the place of their emergence. Their oral history teaches that their ancestors climbed up from the third world into this, the fourth world, through a Sipapuni, or place of emergence, located near the Little Colorado River's confluence with the main Colorado River. This location is holy ground, the physical point of origin for the Hopi people, and the destination of spiritual pilgrimages. The Salt Trail, a treacherous route leading from the rim to salt deposits near the river, is physically real but spiritually charged, requiring mental preparation and adherence to ritual protocols to traverse safely. Similarly, the Zuni people view the canyon as a place of origin and a corridor through which their ancestors traveled. They identify specific landmarks, such as Ribbon Falls and Thunder River, as places of deep historical resonance. The canyon is woven into their prayers, songs, and clan histories. The Havasupai tribe, whose name translates to People of the Blue-Green Water, holds a unique position as the only tribe that still resides within the depths of the Grand Canyon. Their village of Supai, located in Havasu Canyon, a major tributary south of the Colorado River, is accessible only by foot, mule, or helicopter. For centuries, the Havasupai practiced a seasonal migration pattern that perfectly utilized the canyon's vertical geography. In the summer, they lived in the canyon bottom, irrigating crops with the mineral-rich waters of Havasu Creek. In the winter, when the canyon floor lost direct sunlight and became cold and shadowed, they migrated to the plateau on the rim to hunt and gather piñon nuts. This lifestyle was disrupted by the establishment of the park and federal restrictions, which confined them to a smaller reservation within the canyon, but their presence remains a testament to human resilience. Their connection to the water is absolute. The travertine pools and waterfalls of their homeland are not just scenery, but the lifeblood of their culture and economy. To the south, the Hualapai tribe people of the Tall Pines controls the southern rim of the western Grand Canyon. Their connection is rooted in the belief that the canyon was created by a great flood, and that the rock formations represent the spirits of their ancestors. On the north rim and the strip of land to the north, the southern Paiute bands, including the Kaibab Paiute, have utilized the resources of the high plateaus and the canyon depths for millennia. They were masters of wild plant usage, harvesting agave, yucca, and grass seeds. The roasting of agave hearts in large stone-lined pits was a critical subsistence activity. These roasting pits, still visible today as mounds of fire-cracked rock and ash, utilize the agave plant which is native to the canyon. The agave crowns were slow roasted for days to break down complex carbohydrates into digestible sugars, providing a sweet, calorie-dense food source that could be dried and stored. This practice demonstrates a sophisticated understanding of botanical chemistry and thermal regulation. The environmental context in which these cultures thrived is driven by the dynamic climate of the canyon. The Grand Canyon acts as a massive drain for the Colorado Plateau, but it also generates its own weather. The seasonal rhythm is dominated by the North American monsoon, a meteorological phenomenon that defines the late summer. During June, the canyon is typically at its driest and hottest, with the sun baking the rock layers. As July approaches, a shift in wind patterns draws moisture northward from the Gulf of California and the Gulf of Mexico. The intense heating of the canyon walls creates thermal columns of rising air. When this rising hot air meets the incoming moisture, it cools and condenses rapidly, forming towering cumulonimbus clouds. The result is violent, localized thunderstorms. These are not gentle rains. They are deluges. A storm might dump inches of rain on a specific mesa while leaving the adjacent canyon completely dry. The hydrology of these monsoon storms is sudden and terrifying. Because the desert soil is often baked hard or composed of bare rock, it cannot absorb water quickly. The runoff funnels into slot canyons and dry washes, creating flash floods. A dry stream can transform into a wall of water, mud, and debris, moving at highway speeds in a matter of minutes. These floods are a primary geomorphic agent in the side canyons, scouring the bedrock and moving massive boulders. They are also a critical source of water for the potholes and tenajas, natural rock basins that hold water long after the rain stops, sustaining wildlife in the arid zones. Winter in the park presents a dichotomy of extremes. The North Rim, sitting at 8,000 to 9,000 feet, receives heavy snowfall, often exceeding 100 inches a year. The road to the North Rim is closed from late autumn to late spring, buried under drifts. This snowpack is the life support system for the region's hydrology. As the snow melts slowly in the spring, the water percolates through the porous Kaibab limestone. It travels downward through the rock layers until it hits the Coconino sandstone and eventually the impermeable Bright Angel shale. This slow-motion groundwater movement feeds the springs that burst forth from the canyon walls thousands of feet below. Without the heavy winters on the North Rim, the hanging gardens and tributary streams in the canyon would dry up. Conversely, the South Rim receives less snow, and the inner canyon at river level almost never sees snow accumulation. It is possible to stand in a blizzard on the rim and look down to see sunlight hitting the cactus on the Tonto platform, a visual demonstration of the adiabatic lapse rate, where temperature increases as elevation decreases. The wildlife that navigates this complex climate has evolved specific physiological and behavioral adaptations. One of the most fascinating small mammals in the park is the ringtail. Often called the ringtail cat, it is not a cat, but a member of the raccoon family. With large eyes adapted for night vision and a tail longer than its body, the ringtail is a master climber, capable of ascending vertical canyon walls and shimmying up narrow chimneys of rock. It can rotate its hind feet 180 degrees, allowing it to descend headfirst like a squirrel. Ringtails are strictly nocturnal, avoiding the searing heat of the day by sleeping in rock dens. They are omnivorous opportunists, feeding on insects, lizards, berries, and rodents. Historically, miners and early settlers kept ringtails as pets to keep their cabins free of mice, earning them the nickname miner's cat. The bat population of the Grand Canyon is remarkably diverse, with 22 documented species living within the park. The canyon's vertical walls offer infinite roosting opportunities in cracks, crevices, and caves. The canyon bat is the smallest, fluttering like a butterfly in the twilight. The big free-tailed bat is a strong flyer, foraging high above the canyon rims. These animals are the primary nocturnal insect control force. They face a unique challenge in the canyon: the complex acoustics. Echolocation signals bounce off the myriad cliff faces, creating a clutter of echoes. Canyon-dwelling bats have evolved to interpret this complex auditory landscape to pinpoint a moth or mosquito against a background of stone. They are also vital pollinators for agave and saguaro plants, playing a crucial role in the reproductive success of the desert flora. Reptiles in the canyon are governed by the sun. The Grand Canyon pink rattlesnake is a subspecies of the western rattlesnake found nowhere else on Earth. Its color has evolved to match the reddish hue of the local rocks, providing perfect camouflage against predators like hawks and owls. This snake is pit viper, equipped with heat-sensing pits between its eyes and nostrils that allow it to detect the thermal signature of a mouse in total darkness. Its venom is hemotoxic, designed to digest the prey before it is even swallowed. Another arachnid resident, the bark scorpion, is the most venomous scorpion in North America. Unlike other scorpions that are solitary, bark scorpions are known to congregate in winter, huddling together in clumps of 20 or 30 individuals to share body heat, a behavior known as aggregation. This survival strategy allows them to endure the freezing winter temperatures of the upper canyon slopes. The most dramatic insect interactions in the park involve the tarantula and the tarantula hawk. The tarantula hawk is a massive wasp with metallic blue-black body and bright orange wings. It is a parasitoid. The female wasp hunts tarantulas, which are significantly larger than she is. When she finds one, she stings it, delivering a potent neurotoxin that permanently paralyzes the spider but does not kill it. She then drags the immobilized spider to a burrow, lays a single egg on its abdomen, and seals the entrance. When the egg hatches, the wasp larva burrows into the living spider and eats it from the inside out, saving the vital organs for last to keep the meat fresh. This macabre life cycle is a stark reminder of the intense biological pressures in the desert environment. The Colorado River ecosystem, modified by the Glen Canyon Dam, continues to be a focal point of scientific study and management. The temperature of the water is a critical variable. Native fish, like the humpback chub, require water temperatures of at least 16 to 17 degrees Celsius to spawn successfully. The dam releases water that is consistently around 8 to 10 degrees Celsius. This thermal shock prevents eggs from hatching and larvae from surviving. To mitigate this, scientists have experimented with bug flows, steady low flows on weekends, to ensure that insect eggs laid at the river's edge remain submerged and hatch, providing food for fish, and high-flow experiments designed to mobilize sediment. Sediment is the currency of the river. Before the dam, the river carried millions of tons of sand and silt. This sediment built camping beaches, created backwater habitats for young fish, and protected archaeological sites from exposure. Today, the dam traps 95% of the sediment upstream. The beaches are eroding, and the wind no longer blows enough fresh sand to cover and protect the ancient pottery and masonry buried in the dunes. The high flow releases mimic natural floods, pushing sediment from the riverbed up onto the banks, temporarily rebuilding the beaches and habitat complexity. This interplay of ancient culture and modern ecology defines the Grand Canyon. It is a place where a split-twig figurine found in a cave speaks to the same scarcity and reverence for life that a biologist feels when monitoring the flight of a California condor. The condor, with its naked head and 9-foot wingspan, is a living link to the Pleistocene, yet its survival depends on modern radiotelemetry and lead-free ammunition initiatives. The Havasupai irrigator directing water to a corn patch is engaging in the same hydrological relationship with the canyon as the park engineer managing the wastewater treatment plant on the south rim. The landscape commands adaptation. Whether it is the physiological adaptation of a kangaroo rat's kidneys to conserve water, or the cultural adaptation of the Puebloan people building south-facing cliff dwellings to capture winter sun, the lesson of the Grand Canyon is one of fitting into the mold of the environment. It is a testament to life's ability to persist in the face of overwhelming geological indifference. The wind that carved the Coconino sandstone is the same wind that disperses the pollen of the cliff rose. The gravity that pulls down the rock falls is the same force that brings the snowmelt to the springs. In the Grand Canyon, nothing exists in isolation. The rock, the water, the wildlife, and the human history are fused into a singular, colossal reality. Just as the biological and cultural narratives of the Grand Canyon depend on the physical stage set by the Earth, that stage itself is the result of a violent and complex tectonic drama that predates the existence of any observing eye. To understand the Grand Canyon in its totality, one must peel back the thin veneer of the present biological moment and descend into the mechanics of planetary construction and destruction. The silence of the canyon today belies the cacophony of its formation, a saga of colliding continents, warm shallow seas, howling sand dunes, and the relentless hydraulic power of a river fueled by the melting snows of the Rocky Mountains. The transition from the living ecosystem to the lithified record is not a change of subject, but a shift in timescale. The rock layers are simply ecosystems of the past, frozen in stone, waiting to be read by those who understand the language of geology. The foundational story of the Grand Canyon begins in the Granite Gorge, the deepest and oldest section of the park. Here, the Colorado River scours against the Vishnu basement rocks. These rocks, dating back approximately 1.7 to 1.8 billion years to the Paleoproterozoic era, are not sedimentary layers laid down by gentle waters. They are metamorphic and igneous rocks, the scar tissue of the North American continent. They began their existence as sedimentary and volcanic deposits in a marine basin, but roughly 1.7 billion years ago, a massive plate tectonic collision occurred. A chain of volcanic islands, not unlike modern-day Japan or the Aleutians, crashed into the proto-North American continent. This collision, known as the Yavapai orogeny, subjected the rocks to unimaginable heat and pressure, burying them miles beneath the surface. The intense heat cooked the rock, realigning its mineral structure into the twisted, banded gneiss and schist visible today. Molten magma from the mantle forced its way into cracks in the schist, cooling slowly to form the pink streaks of Zoroaster granite. These rocks represent the roots of a mountain range that likely stood as high as the modern Himalayas. Over hundreds of millions of years, erosion wore these mountains down to a flat plain, removing miles of overlaying rock and exposing the basement core. This cycle of mountain building and subsequent erasure is the first chapter of the canyon's geologic biography. Resting directly on top of these ancient, twisted basement rocks is a geologic feature that represents one of the greatest mysteries in Earth science: the Great Unconformity. In many places within the canyon, the horizontal Tapete sandstone, roughly 525 million years old, sits flush against the vertical Vishnu schist, 1.7 billion years old. The contact line between them is sharp and distinct, yet it represents a missing gap in the geologic record of approximately 1.2 billion years. This is roughly 25% of the age of the Earth, gone without a trace. There are several theories regarding this hiatus. Some geologists suggest that during this missing billion years, the supercontinent Rodinia was forming and breaking apart, and the region was uplifted and eroded. A more recent and provocative hypothesis involves the cryogenian period, often referred to as snowball Earth. This theory posits that the planet underwent a global glaciation, where ice sheets covered the globe from pole to equator. These massive glaciers would have acted as bulldozers, scouring the continental crust down to the bedrock and pushing the debris into the oceans, effectively wiping a billion years of history off the map. When the ice melted and the seas rose, the Tapete sandstone was deposited on the freshly scoured surface. Touching the great unconformity is a tactile encounter with deep time, a physical connection to a billion years of silence. Above this unconformity lies the Tonto group, a sequence of sedimentary layers that chronicles a marine transgression or a rising sea level during the Cambrian period. The Tapete sandstone is composed of coarse, cross-bedded sand, indicating a high-energy environment like a beach or nearshore dune system. As the sea level continued to rise and the shoreline migrated eastward, the water became deeper and calmer. This transition is marked by the Bright Angel Shale, a layer of soft green mudstone that formed in the quieter waters offshore. This shale is rich in fossils, particularly trilobites and brachiopods, signaling the explosion of multicellular life in the Cambrian seas. Above the shale lies the Muov limestone, formed in even deeper water from the calcium carbonate skeletons of marine organisms. This triplet of layers, sandstone, shale, limestone, is a classic textbook example of a marine transgression, capturing the slow drowning of the North American coast over millions of years. The geological narrative then jumps forward, skipping the Ordovician and Silurian periods, another unconformity caused by erosion, to the Redwall limestone of the Mississippian period, roughly 340 million years ago. The Redwall is perhaps the most prominent cliff-forming layer in the canyon, creating a sheer vertical barrier that is often hundreds of feet high. Despite its name, the rock is actually a pure bluish-gray limestone. Its red surface is a stain caused by iron oxide washing down from the rocks above. The Redwall tells of a time when the Grand Canyon region was submerged under a warm, shallow tropical sea, similar to the modern Bahamas. The rock is composed almost entirely of the remains of marine creatures, crinoids, sea lilies, corals, bryozoans, and foraminifera. The sheer volume of biological material required to build this 500-foot-thick cliff is staggering. The Redwall is also significant for its karst topography. Because limestone dissolves in slightly acidic rainwater, the Redwall is riddled with cave systems, sinkholes, and solution caverns, many of which serve as major aquifers channeling water through the canyon walls. Following the deposition of the Redwall, the environment shifted dramatically during the Pennsylvanian and Permian periods. The region fluctuated between coastal plains, river deltas, and dry land. The Supai Group and the Hermit Shale are characterized by their deep red color, indicative of iron-rich sediments deposited in swampy, oxygen-rich environments. These layers contain fossils of ferns, conifers, and dragonflies, painting a picture of a lush, semi-tropical floodplain crossed by meandering rivers. However, the climate was drying out. The overlying Coconino sandstone represents a radical environmental shift to an arid desert. The Coconino is composed of pure quartz sand, frosted by wind abrasion. The rock preserves massive cross-bedding structures, which are fossilized slip faces of giant sand dunes. Paleontologists have found trackways of small reptiles and arachnids preserved in this stone, freezing the moment an animal scuttled across a dune face 275 million years ago. The direction of the cross-bedding allows geologists to reconstruct the prevailing wind patterns of the Permian, showing that the winds blew from the north, carrying sand from as far away as present-day Canada. The capstone of the canyon's sedimentary sequence is the Kaibab Formation, deposited roughly 270 million years ago. This limestone layer records the return of the sea, the final marine incursion before the region was uplifted. The fossils here, sponges, sharks, teeth, and large brachiopods, are marine in origin. It is a profound irony that the highest points of the Grand Canyon, sitting 8,000 feet above sea level, are composed of the floor of an ancient ocean. Following the deposition of the Kaibab, the region underwent a period of massive tectonic uplift known as the Laramide orogeny, occurring roughly 70 to 40 million years ago. This is the event that built the Rocky Mountains. However, unlike the Rockies, which were buckled and folded, the Colorado Plateau was lifted largely intact, rising thousands of feet like a hydraulic elevator. The thick, stable crust of the plateau prevented it from crumpling, preserving the horizontal orientation of the rock layers. This uplift was crucial. It provided the potential energy, the elevation, that would allow the Colorado River to carve the canyon. The carving of the canyon itself is a much more recent event than the rocks it cuts through. While the rocks are billions or hundreds of millions of years old, the Grand Canyon as a landscape feature is likely only 5 to 6 million years old. The mechanism of the river's integration is a subject of intense debate, specifically the Old Canyon versus Young Canyon theories. The current scientific consensus favors a Young Canyon model, where the Colorado River integrated its course roughly 6 million years ago. This likely happened through a process called stream piracy, or headward erosion. An ancestral river flowing from the Rockies likely ended in a closed basin or lake. Meanwhile, a steeper, younger stream to the west was cutting backward, headward, from the Gulf of California. Eventually, this western stream breached the basin, capturing the ancestral river and diverting its flow toward the ocean. This capture dramatically increased the river's volume and gradient, accelerating the downcutting process. The river acts as a linear saw, cutting downward, while mass wasting, rockfalls, landslides, and erosion widens the canyon. The width of the canyon is determined largely by the softness of the rock layers. Soft shales erode back to form broad benches, like the Tonto platform, while hard limestones and sandstones maintain sheer cliffs. The climatic engine that drives these erosional processes is as complex as the geology. The Grand Canyon encompasses a massive vertical relief, which creates distinct microclimates. The temperature increases by approximately 5.5 degrees Fahrenheit for every 1,000 feet of elevation loss. This means the bottom of the canyon is consistently 20 to 25 degrees hotter than the rim. In the summer, the inner canyon is a furnace, with rock surfaces radiating heat long into the night. This heat low creates a thermal trap. Conversely, the rims are high-altitude environments. The North Rim, reaching over 8,000 feet, experiences a subalpine climate. This disparity drives local wind patterns. During the day, the air in the canyon heats up and rises, creating up-canyon winds. At night, the air on the rims cools rapidly and sinks into the canyon, creating down-canyon drainage winds. These diurnal wind shifts are predictable and utilized by birds of prey and scavengers, like the California condor, to gain lift. The seasonal cycle of the park is defined by moisture. Winter brings frontal storms from the Pacific Ocean. These storms must cross the Sierra Nevada and the Basin and Range Province before reaching the Colorado Plateau, so they have often lost much of their moisture, but they still deposit significant snowpack on the north and south rims. This snow is the primary recharge for the regional aquifers. The porous Kaibab limestone acts like a giant sponge, absorbing melting snow. The water travels vertically through fractures until it hits the impermeable Bright Angel Shale, forcing it to flow horizontally until it emerges as springs in the canyon walls, such as Roaring Springs, which supplies water to the entire park via a trans-canyon pipeline. Spring in the canyon is a season of high winds and rapid transformation. As the sun angle increases, the temperature differential between the warming canyon bottom and the still frozen rims creates intense pressure gradients, resulting in sustained winds that can strip moisture from plants and soil. This is the four-summer drought, a critical testing time for plant life before the arrival of the monsoon. The blooming of the cactus and wildflowers in the inner canyon occurs months before the flora on the rim wakes up, creating a green wave that travels upward in elevation as the season progresses. The North American monsoon, arriving in July and August, changes the dynamic completely. High pressure sets up over the southern United States, reversing the wind flow and drawing deep subtropical moisture from the Gulf of California and the Gulf of Mexico. This moisture clashes with the superheated air rising from the canyon, creating violent convective thunderstorms. These storms are characterized by intense lightning frequencies and torrential, short-duration rainfall. Because the desert soils are hydrophobic, water repellent, and vegetation is sparse, the runoff is immediate. Dry washes that have not seen water for months become raging torrents of mud, boulders, and logs. These flash floods are the primary architects of the side canyons. They scour the bedrock, rearrange debris fans at the river's edge, and replenish the nutrients in riparian zones. The sound of a flash flood, a low-frequency rumble often described as sounding like a freight train, is a warning signal that reverberates through the narrow slots. The ecosystem response to these geological and climatic variables is one of extreme specialization. The concept of refugia is critical in the Grand Canyon. Because the landscape is so broken and varied, it creates isolated pockets where species can survive outside their normal range. For example, during the last ice age, the canyon was cooler and wetter. As the climate warmed, cold-loving plants and animals retreated. They couldn't move north fast enough, so they moved up or into the shadows. Today, on north-facing slopes, which receive less direct sunlight, and in deep shaded alcoves, one can find species of fir and spruce that typically belong hundreds of miles to the north. These are relict populations, stranded islands of the Pleistocene surviving in the shadows of the cliffs. One of the most specialized habitats in the park involves the hanging gardens. These occur where groundwater seeps from the canyon walls, usually at the contact point between the Coconino Sandstone and the Hermit Shale, or the Muav Limestone and Bright Angel Shale. In the middle of a vertical red rock desert, these seeps support lush mats of maidenhair fern, crimson monkeyflower, and golden columbine. These microecosystems are fragile and entirely dependent on the hydrogeology of the rim above. They serve as critical watering stations for pollinators and birds. The McDougall's flavuria, a rare plant found in these seeps, exists nowhere else on Earth. Its survival is inextricably linked to the groundwater pressure, maintained by the snowmelt thousands of feet above. The interactions within these ecosystems are governed by the availability of water and the extreme temperature gradients. The biological crusts of the soil, composed of cyanobacteria, are the unsung heroes of the high desert. When wet, These microscopic filaments expand and become active, fixing nitrogen from the air and binding soil particles together to prevent erosion. When dry, they go dormant, turning black and brittle. They create a textured, knobby surface that increases water absorption during rain events. Without these crusts, the soil would wash away, and the pinyon juniper forests would collapse. The pinyon jay and the pinyon pine share a mutualistic relationship that underscores the interconnectedness of the rim ecosystem. The jay harvests the pine nuts, which are rich in fats and proteins, and buries them in thousands of caches to survive the winter. The bird has an incredible spatial memory, recovering most of the seeds. However, the ones it forgets germinate and grow into new trees. The distribution of the pinyon forest is thus largely driven by the flight patterns and memory lapses of this specific bird. Fire's another abiotic factor that shapes the landscape, particularly on the rims. The ponderosa pine forests of the transition zone are fire-adapted ecosystems. Historically, frequent, low-intensity fires caused by lightning swept through these forests every few years. These fires burned the grass and pine needles but left the mature trees, with their thick, puzzle-piece bark, unharmed. This kept the forest open and park-like. Decades of fire suppression in the 20th century led to an accumulation of fuel, increasing the risk of catastrophic crown fires that can sterilize the soil and kill the old-growth trees. Modern park management utilizes prescribed burns to mimic the natural fire cycle, restoring the ecological balance. The interplay of fire and rock is visible, where the limestone cliffs stop the spread of flames, creating natural fire breaks that preserve patches of ancient vegetation. The aquatic ecosystems of the tributaries offer a stark contrast to the main stem of the Colorado River. Streams like Bright Angel Creek, Shanumo Creek, and Tapeats Creek are clear, cold, and spring-fed. They support distinct populations of invertebrates, such as the Grand Canyon obscure skiffle beetle. These tributaries are also the breeding grounds for the native fish that struggle to survive in the altered main river. The flash floods that scour these creeks are actually beneficial in the long term. They flush out fine sediment and expose the gravel beds that native trout and suckers need for spawning. However, these floods also pose a risk to the introduced trout species, which are less adapted to the violent hydraulics of desert streams than the native fish, which have evolved humps, keels, and streamlined bodies to navigate the turbulence. The Grand Canyon is, therefore, a place where the physical earth exerts a direct and undeniable control over the biological world. The chemistry of the Redwall limestone determines the pH of the water in the caverns, which in turn dictates which species of amphipods can survive in the dark. The angle of the sun hitting a south-facing slope creates a microclimate that allows desert agave to grow at elevations where snow falls just a few hundred yards away on the north face. The geological uplift of the plateau created the gradient for the river. The river cut the canyon influenced the local weather, and the weather selected the flora and fauna. It is a cascade of cause and effect that began with the collision of tectonic plates 1.7 billion years ago and continues with the monsoonal thunderstorm developing over the south rim this afternoon. And so the canyon stands not as a monument to the past, but as an argument unfolding in the present tense. Every ledge, seep, and shadow is a sentence still being written, shaped by forces older than life yet responsive to the next cloudburst, the next seed carried on the wind, the next degree of warming or cooling. What happens here tomorrow will not be accidental. It will follow from stone, water, heat, and time, just as it always has. The Grand Canyon reminds us that landscapes are not scenery, but systems, and that the future of rivers, of species, of ourselves will be decided by chains of cause already in motion, waiting only for gravity, sunlight, and rain to continue their work.